So, how do we tie all this together? Well, here's how, folks. If you were wondering how we could tie the last two chapters together with this, well, you don't have to wait any longer. Um, if we have a positive voltage, okay, if we have a positive voltage, then that means the reaction is spontaneous. So that would be a negative delta G. So a positive E cell, that reaction is going to have a negative delta G, which means the product side is favored, right? Which means you're going to have an equilibrium constant that is greater than 1. So all that being said, I'm going to try to type this out for you. Here's what that means. If E cell is positive, then delta G is negative, and the equilibrium constant way greater than 1, or greater than 1. The opposite is also going to be true. If we draw a galvanic cell and we see that the voltage is negative, then that means it's non-spontaneous in that direction, which means delta G is positive, which means the reactant side is favored, which means the equilibrium constant is less than 1. So if the voltage for your galvanic cell is negative, then delta G must be positive, non-spontaneous, and the equilibrium constant must be, whoops, less than 1. Whoops. So that's how they're all related. We talked about the relationship between delta G and the equilibrium constant back in Unit 17, okay, last week. Spontaneous means product side is favored, equilibrium constant greater than 1. Now we're just adding another piece to it. That would also be a E cell that's positive, okay? And then the opposite is also true. So make sure you know how they're all related, right? This is really the slide that ties the last, 3 chapters we do together. This ties electrochemistry, thermochemistry, and equilibrium all together. Yeah, kind of a big deal. So what if we are not under standard conditions? So what does this standard mean? So if you look at E cell, like what does this little degree sign mean? Well, this little degree sign, remember if you back in thermochem, we had that thermochemical standard, right? Like the delta HF standard. Okay, that means 25 degrees Celsius, 1 molar concentrations of everything, right? So 1 molar concentration of everything, 25 degrees Celsius. And if it's a gas, it would be 1 atmosphere of partial pressure for everything. So the same as the thermodynamic stuff. But, what if I don't want to run my battery with 1 molar concentrations of everything, right? What if I don't want to run my battery, and again, batteries with gases, right? That just kind of blows my mind. It can be done, but anyway. What if I don't want to have a partial pressure of 1 atmosphere? How can I predict the voltage of a battery under non-standard conditions? Well, here we go. The voltage, or E cell non-standard, is equal to E cell standard minus a constant, 0.0592, divided by the number of electrons in the balanced redox equation times the log of the reaction quotient. Oh my goodness. This is called the Nernst equation. It's called the Nernst equation. Nernst was a German scientist, by all accounts, not a very nice guy, but anyway. He's kind of that World War I, World War II kind of time for Germany, if you catch my drift. Anyway, so this is this equation, before we even do it, allows us to predict the voltage if I have concentrations that are not 1 molar. Now, because the reaction quotients here, you're writing a mass action expression. Product concentrations raised to their coefficients divided by reactant concentrations raised to their coefficients. That's what's going in here. And then this N on the bottom is when you have the balanced redox equation, what's the least common multiple, right, for your electrons, okay, when you balance that. So a lot going on here. We got to practice. I want to predict the voltage for this battery here. Okay, if we look at this battery, this would be your standard zinc copper battery. And this is actually the first battery you're going to build in lab tomorrow night. It's standard because, excuse me, the concentration of the zinc ions is 1 molar, and the concentration of the copper ions is 1 molar. So we have 1 molar concentration of our aqueous things, right? So that's standard conditions. If you look at this battery over here, you can see the zinc is 0.010 and the copper is 2 molar. So we've decreased the amount of zinc and we've increased the amount of copper. And if we do the Nernst equation correctly, we should get 1.17 volts. I mean, let's see. So give me a second here. I'm going to write this information down on the board. Cool. So here we go. Let's start by writing down the Nernst equation. And that says E cell non-standard equals E cell standard minus 0.0592 over n times the log of Q. So we're given E cell standard, although you could use the standard reduction potentials to get it. It is 1.10 volts. So we have that. So now we need N. We need the number of electrons, right, from the balanced equation. So we could break this up into the 2 half reactions if we had to, okay? But if you look at it, it's 2 electrons, right? Zinc goes to zinc plus 2 electrons. Copper plus 2 electrons goes to copper. My N value is 2 for N. And now we need to solve for the reaction quotient Q. We need to write a mass action expression. So that's going to be the zinc concentration over the copper concentration. Remember, solids don't go into the mass action expression. So my mass action expression is the zinc ions over the copper ions. Just like that. So here we go. E cell equals 1.10 volts minus 0.0592 over 2 times the log of the zinc concentration on top, 0.010, and the copper concentration on the bottom. And luckily, since the coefficients are 1, they're all to the first power. So you don't have to worry about that. So now we're going to pop it in there and see if we get that 1.17, which was on the slide. Watch out for order of operations. You know, we want to do all that before, you know. And we get, and if you've done this correctly, take your time, you should get 1.168 or 1.17 volts. That would be the voltage. Now, you can kind of use Le Chatelier. I know, crazy, all comes back to equilibrium. You can kind of use Le Chatelier's principle to predict if your voltage is going to go up or down. Here's how it works, right? If you have a positive voltage, think of your voltage as a product. And how do you make more product? How do you shift the equilibrium position to the right? Well, if I add copper, that shifts it away. Or if I take zinc, that shifts it away. Both of these things happen here. Remember, the standard concentrations are 1 molar. Okay, so what did we do? Well, we dropped the zinc, that pushed it that way. And we increased the copper, that pushed it back. Both of those worked together, okay, to push the reaction to a higher voltage. So you can use the Chatelier to predict whether or not the voltage will go up or down, and you can use the Nernst equation to get the new voltage. Awesome. Here's a much tougher one, folks. If you can do this one, you're in good shape, okay? Here's what I want, okay? I would like you to take this redox reaction, and I would like you're going to need your standard reduction potential table. I would like you to do a couple things. Number 1, can you get E cell standard? Okay, so ignore these kinds. So let's ignore that concentration. Whoa, too much, folks. We're going to ignore that concentration for a minute. We're going to ignore these concentrations for a minute. I want you to put these two together, okay? Finding the least common multiple with the electrons. and I want you to write a balanced redox reaction, put them together, and then I want you to go to the standard reduction potential table, find the standard reduction potentials, and try to predict E cell standard. Then we're going to mess with the concentration. So go ahead. I'm going to copy all that down. All right. So hopefully you put it together. We got to multiply the copper half reaction by 3 and the permanganate half reaction by 2. My least common multiple, my N in this reaction is going to be 6. That's going to be important in a moment when we Nernst this thing. But the first thing we need to do is get E cell standard. So what's E cell standard? Well, we got to go to the table. You are not going to find the copper reaction like this. You're going to have to flip that voltage. So if we look in here, we're looking for copper plus 2 electrons goes to copper, this guy, but we got it in reverse. That's negative 0.34 volts. So that's a negative 0.34 volts. And now the permanganate half reaction, we got to find, where the heck is that? Oh my God. Oh, this guy, right? Be careful. Don't grab the wrong one. You want that one, not the one below it. 4 electrons in. So that's 1.68 volts. That's a positive 1.68 volts. So let's get E cell standard now. We're going to add those two voltages up, the negative 0.34 and the 1.68. And that's a positive 1.34 volts. That's my E cell standard. Okay, now I want you to use the Nernst equation, which is E cell non-standard equals E cell standard minus 0.0592 over N times the log of Q. I want you to use that if we change the concentrations for the aqueous things to 0.01 molar for copper plus 2, 2 molar for permanganate, and we keep the H plus 1 molar. Go ahead, folks, see if you can't get that new voltage. All right, folks, I haven't punched it in yet, but here's what I got. I got 1.34 for my E cell standard. I got an N of 6. And then for Q, we had to write the mass action expression. Well, remember, you got to use the full balanced equation. So that's the copper plus 2 concentration cubed divided by the permanganate ion concentration squared times the H plus ion concentration to the 8th. And what we end up with is 0.010 cubed divided by the quantity 2 squared times 1 to the 8th. Okay, times 1 to the 8th. So here we go, folks. I'm going to try and type this in. Oh, boy. And I got an E cell of 1.41. Now, let me check that. Hang on. You can see how, this is where the electrochemistry chapter and the equilibrium chapter are coming together, right? You got to be able to write mass action expressions, okay? And when we run something under non-standard conditions, what's happening to the voltage? Now, I don't know if we could predict this with Lechat. We could try it. So what has happened here? Well, the copper concentration has gone down and the permanganate concentration has gone up. So yes, both of those things shift the voltage to the right. The voltage should be higher than the standard voltage of 1.34 volts, and we go up to 1.41 volts.